My name is Desmond Kirkpatrick, and today I will present a case to use software-driven design for domain-specific compute. The end of Dennard scaling has moved our industry to target domain-specific accelerators to gain much higher overall compute efficiency. The challenge is that these domains can be quite narrow, with lower volume demand than general-purpose compute. Their high degree of specialization, especially in enabling software, means the primary challenge in this new era of compute is NRE cost reduction. We think a major way to reduce design NRE is to drive accelerator hardware design from a software-first approach, leveraging agile software hardware co-design methods. For this position, here are some assumptions we make about the accelerator market. First is single-purpose accelerators are pretty rare and becoming more programmable to target broader markets. Constellations like for media or AI or data transport are more common, sharing related capabilities in software and hardware. Accelerators are always part of a larger system, both in terms of the Amdahl limit, interaction with other accelerators, as well as their software ecosystems. Separate, highly specialized software stacks often require specialized engineering talent to support. And workloads evolve rapidly, making time to market even more important to viability, as we must quickly add enabling features. Here are some of the ways we can reduce design NRE in domain-specific compute. We can use configurability and scale or feature set to target different markets, complexes that can share common hardware and software infrastructure and support a broad swath of a compute domain, domain-specific hardware libraries to allow for rapid integration of new accelerator IP, investing in domain-specific compiler frameworks. Future-proofing system attach can make it easier to enable capabilities in later generations. Trading efficiency for broader support can amortize the NRE, and co-design methodologies that allow us to quickly arrive at efficient software-hardware trade-offs to lower the NRE of product development. Here's a template of a design flow for domain-specific compute we have been exploring at Intel. On the left, you see a template software-hardware stack. In any given domain, we can envision a compiler library supporting compilation steps to various hardware targets in this domain. We can envision different architectures using parameterized templates. These architectures can range from a simple FSM to a fully programmable microcontroller. And the key blocks are the sequencer, the memory system interface, and the compute engines. Finally, we see that these different architectures can be most quickly assembled from common domain-specific building blocks using these agile hardware design techniques. On the right, we see a representative design flow where we first select an architectural template and concretize it, producing both a customized compiler and hardware target on which we run workloads through simulation or FPGA. But the real unification happens when we use agile techniques to combine design of both software and hardware features and use this design loop to support an always alive, end-to-end, feature-by-feature co-design methodology. This design flow supports design space exploration, system validation, and performance tuning. On the next two slides, I'll show an exemplar for this methodology that is in the open source, a highly configurable, tuned inference engine. The Temporal Virtual Machine, or TVM from University of Washington, is a good exemplar for our template design flow, targeting accelerators in the inference domain. Here we see that the accelerator design stack in this case is comprised of the TVM compiler, the versatile tensor architecture, VITA, and its chiseled building blocks. We have a tensor compiler with configurable passes, an extensible ISA to allow for feature addition, a fully parameterized microarchitecture built from parameterized building blocks, auto-tuning to support design space exploration, and finally FPGA support for long workloads. Here we show just how flexible this stack is for design space exploration of the VITA microarchitecture. We generated Pareto optimal designs around 3 target operating points illustrated here. For example, in the largest case, we configured a wider memory interface to feed this higher throughput inference engine. If VITA is our architectural template, we have shown that we are able to keep a full stack running while reconfiguring and adding features to this design using agile software hardware co-design techniques. And our experiences are documented in the archive reference in the abstract. In summary, addressing the question, what kinds of EDA innovation do we need to support domain-specific compute? We see the need for software hardware co-design methodologies, especially those that bring the benefits of software methods to integrate the hardware side and run at the speed of software. Compiler technologies that enable hardware decision-making, and really good examples of these technologies are the Halide language, the TVM framework that I showed earlier, MLR infrastructure, and a new language called EXO that works on linear algebra type of computation. We see a need for design space exploration support, as these spaces are new and don't have the benefit of legacy design. There's the old adage that the microprocessors benefit from all the big iron mainframe research of the 60s and 70s, like the Tomasulo algorithm. A few techniques that can help DSC are a parameterized design, both in software and hardware, very rapid backend feedback. Perhaps we use machine learning predictors here, and search space support. Again, maybe machine learning can help us here. Finally, having building block libraries, especially those that have domain-specific knowledge baked in, can really help build domain-specific architectures quickly. For example, a Formula One engine can be swapped in hours, for example, in the middle of race tuning.